so hydrogenation. Okay, we're adding hydrogen to the carbonyl group or carbonyl group. This is a ketone. If this was a hydrogen, that'd be an aldehyde. Okay, but this is the ketone here. So we're adding hydrogen across the bonds. We're going to add a hydrogen to here. Open this bond up. Electrons go here. And add a hydrogen to here. Okay, so it splits this bond here. So one goes up here. The other one goes to the carbon of the carbonyl group. So a ketone with hydrogenation always produces a secondary alcohol. An aldehyde would produce a primary alcohol. A ketone would produce a secondary alcohol. Right? And that's what we got over here. Okay. Okay. So write an equation. So the hydrogenation of 3-pentanone. 3-pentanone is ONE ending means a ketone. Pentane means 5 carbons, single bonds, and the carbonyl group is located at number 3. So let's put it up here. Let's put CH3, CH2, C. There's your carbonyl group. CH2, CH3. That's pentanone. Okay. Hydrogenation means just adding hydrogen across the double bond. Okay. So it's going to add to this oxygen and to that carbonyl carbon. So it's going to end up with CH3, CH2. We open up this bond. Okay, and we add our hydrogen, and we add our hydrogen to the carbon. And we have a secondary alcohol. Okay, so we have an, because adding hydrogen is reduction, right? Oxidation is adding oxygen, reduction is adding hydrogen. So the reduction of a ketone is always going to produce a secondary alcohol. And this would be 3-pentanone, pentanol, 3-pentanol would be the product of that reduction. Okay, so this is 3-pentanone. We're adding hydrogen. Again, it's going to attack. The hydrogen is going to go to the oxygen here because this bond's going to open up, bring electrons here and here. And then the other hydrogen of the H2 is going to attach to the carbon. Right? As we covered last time. Is that all making sense? I think people nodding their heads.
Yes, it is.
All right, perfect. Okay, so 3-pentanol. Okay, right equation for hydrogenation of propanone and butanone. So propanone is 3 carbons, butanone is 4 carbons. Okay, so propanone would be CH3, C double bond O bonded to CH3. That's propanone. And hydrogenation is adding H2. And you can open up that double bond. Okay, and add a hydrogen to the oxygen and a hydrogen across there. And that's your chemical equation for the hydration of propanone. Okay. So the reduction of propanone produces a secondary alcohol, which is propanol, 2-propanol. Let's write that here. Here's a little more clear picture of it. But you can see the hydrogen is going to attack the oxygen and then the carbon of the carbonyl group. And this is propanol, and the OH group is in the number 2 position. Okay. And then butanone, or that's 2-propanol. Okay. Okay, so butanone is 4 carbons. The carbonyl group is at number 2 because it has to be. Okay, if I put it here, it would be an aldehyde. If I put it here, it'd be an aldehyde. If I put it here, it'd still be number 2 position. Because you always give the carbonyl the lowest possible number. So you don't need to put 2 butanone because there's only one place it can be. So there's butanone. We're going to add hydrogen across our double bond, hydrogenation reaction, one at each end of the double bond. So here's our OH group, and here's our H group. Okay. So who wants to name the product of the reduction of butanone? What's it produce? What's the name of this thing right here?
2-butanol.
Perfect. 2-butanol. Okay. 4 carbons. It's an alcohol. And the OH group is at the number 2 position. Okay. All right. Don't worry, it's going to get hard. This will probably be the most confusing part. There's going to be a lot of new terminology and things you're not familiar with. So it's going to get a little bit tougher here as we go along, but I'll explain it and we'll go through it nice and slow for you. So if you have problems, ask questions or raise your hand up. Okay, or put it in, I got the chat window open too. So the hydrogenation of an aldehyde, okay, results in production of a primary alcohol. So reduction or hydrogenation of an aldehyde results in a primary alcohol. Okay. And this is where we do the reduction of butanal. Okay, butanal is an aldehyde because it has an Al ending rather than O and E. O and E was a ketone. Al is an aldehyde. Ol is an alcohol. Okay, butanal is 4 carbons, which you got right here. Okay, when it's an aldehyde, it's on the very end because there's an H on the end, hydrogen terminal. So it's the carbonyl group is at the last, or in this case, the first carbon. Okay, you always start numbering your carbonyl group. So we're going to add hydrogen across the double bond there. So here's our 1 hydrogen, adds to the oxygen, our other one added to the carbon. Okay. So reduction of a ketone gave us a secondary alcohol. Reduction of a aldehyde gives us a primary alcohol. And this would be 1-butanol. Okay, which is a primary alcohol. All right. Radical hydration of 3-methylbutanol. So you have to know what methylbutanol looks like. So again, working backwards, we know that's an aldehyde. So we know our carbonyl groups on the very beginning or the very end of when we write the compound out. Then butane is 4 carbons. So we have carbon, 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 carbon. And we know this one on the end is our aldehyde. Okay, that's butanal. And then number 3 carbon, remember the carbonyl group is always number 1. So this is 1, 2, this is number 3, there's a methyl group. So this is CH3, this is CH, this is CH2, and our carbonyl group. Those didn't really go very well there. I made it kind of unclear. Okay, so there's our methyl group. And we'll just put our hydrogens here. Okay, and every one of these is a hydrogen. Okay, so that's 3-methylbutanol. Hydrogenation. Hydrogenation means we're adding hydrogen plus H2. Okay. So again, hydrogen is going to, this double bond is going to open up right here. Electron's going to go to the oxygen and to the carbon. Okay, that's going to allow hydrogen to attach at each end of the double bond. So we're going to end up with CH3, CH3, CH2, C, our double bond's going to open up here. We're going to add our hydrogen and our hydrogen, and then hydrogen. Okay, so now we've ended up with 3-methyl 1-butanol. Okay, as our product. Okay, so here's our 3-methyl butanol. This compound right here. Here's our carbonyl group. Okay, we're going to add hydrogen across each side of the double bond. So we have our OH and our H. That's what we've added. Okay, and we said it was 3-methyl butanol, or 3-methyl 1-butanol. Okay. Write the equation with hydrogenation of 3,4-dimethyl hexanal. Okay. And 2-chloropentanal. So two equations here. First one we're going to do is 3,4-dimethyl hexanal. So the Al ending means it's an aldehyde. Okay. And hydrogenation means you're adding hydrogen. That's reduction. When we reduce an aldehyde, what do we get? Our product is going to be a primary acid. Okay, so aldehydes by hydrogenation are going to give us a primary acid. So our answer better be a primary acid. Okay, so hexanal is 6 carbons. And let's do it on 1, 2, 3, 4, 5, 6 carbons. Okay, and it's hexanal. So this is our aldehyde group here. Okay, so 3,4-dimethyl hexanal plus hydrogen. Okay, it's going to go to 1, 2, 3, 4, 6 carbons again. Okay, and on this one we're going to have our OH, and then our carbon, our 1, 2, 3, 4 dimethyl, using line diagrams. And that's what we produce. Right. So this is it drawn out, the structural formulas. Okay, this is our carbonyl carbon right here. It's 6 carbons. And numbers 3 and 4, there's a methyl group. So our hydrogen is going to tack that double bond onto each side of it, and it's going to produce our OH group and our hydrogen. Same thing as the line formula above it. It's a primary alcohol. Okay, and it's hexanal. Okay, 3,4-dimethyl 1-hexanol. Okay. 6 carbons with our alcohol at the number 1 position, OH group, and then there's a 2 methyl groups, 1, 3, 1, and 4. 2-chloropentanol. Pentanol is 5 carbons with a chlorine group at number 2 position. Okay. So here's 5 carbons. 1, 2, 3, 4, 5 carbons. At the number 2 carbon, there's a chlorine group. Okay. And it's an aldehyde. So we know it's going to produce a primary alcohol. So again, we open up as a double bond. Hydrogen goes to here. Hydrogen goes to the carbon. Okay. Each side of the double bond. So we got our hydrogen attached to the oxygen and our hydrogen attached to the carbon. Okay. So now we've got a primary alcohol. And this primary alcohol is 2-chloral, because there's a chlorine group at number 2. Okay, 1. And how many carbons do we have? 5. So pentanol. Pentanol. O-L ending. Okay. 2-chloral, 1-pentanol. Making sense? Someone give a thumbs up or a nod or a yes. All right, perfect. All right, a biological example, which you're going to be using in biochemistry when we start chapter 16, okay, is reduction of a ketone occurs in the body during strenuous exercises. When the lungs and circulatory system not be able to provide enough oxygen, to your muscles, your body goes into what's called aerobic respiration, anaerobic respiration without oxygen. And it starts to break down glucose without using oxygen. It's not as efficient and different byproducts are produced. And we go into this. So under those circumstances, lactate formation begins, which is anaerobic metabolism, which means we're breaking down glucose to provide energy without the presence of oxygen. Because the body can't deliver oxygen fast enough for the muscle to keep using it. So now it goes and it switches to anaerobic metabolism, which I said is not as efficient. Okay, so in the reaction, the enzyme lactase dehydrogenase reduces pyruvate. Okay, the product of glycolysis. Okay, it's a pathway to break down the glucose into lactate. So in anaerobic metabolism, glucose breaks down to pyruvate, and pyruvate breaks down further to give us anaerobic metabolism, and it produces lactic acid or lactate. Okay, so lactic acid is what builds up in your muscles in anaerobic metabolism. The source for hydrogen is nicotinamide adenine dinucleotide, NADH. And we're going to see a lot of NADH as you guys are going through biochemistry. Because NADH provides a hydrogen to use in reduction reactions. Okay? So NADH loses hydrogen, so it's being oxidized, so you get reduction of the other compound. In this case, it's glucose. Okay, so here's pyruvate. That's what pyruvate looks like. 3 carbons and 2 carbonyl groups. Okay. NADH is going to donate hydrogen. It's going to lose a hydrogen. So it's going to attack the double bond. It's going to put a hydrogen here and a hydrogen here. Okay. So it's going to take 2 NADH molecules to do that. Okay. It's just like adding hydrogen, just like we did before. The same exact thing, except now we're doing it inside the human body. Okay, so we produce what's called lactate or lactic acid. Okay, there's your OH group, there's your H, and the rest of the structure stays the same. Okay, this is lactic acid. You ever have muscle cramps? Okay, you ever exercising, all of a sudden you just can't go any further. Muscles cramp up, that's lactic acid buildup. The lactic acid builds up and just says, you either doing anaerobic metabolism, you just can't do anymore. There's just not enough left over. The lactic acid starts to cramp up your muscles and slow your body down. So you can catch back up again. Okay. That's a biological example of reduction that we've been doing with basically hydrogenation. We're adding hydrogen across a double bond, but we're using NADH as our hydrogen donor. That's giving us the hydrogen we're going to use to have hydrogenation across that double bond. So again, NADH goes to NAD+. So that's lost the hydrogen. So NADH is being oxidized. Okay? If something else is being oxidized, something else has to be reduced. And pyruvate is being reduced. You're adding hydrogen. Okay? Those are all terms we've been familiar with before. They said now we're just seeing it in the body is producing what's called lactic acid, which causes your body to cramp up and stop exercising. All right, so label each of the following as an oxidation or reduction reaction. And give you the answer before I give you the question here. Okay. Pretend you don't see the right-hand side. That's okay. Ethanal goes to ethanol. Ethanal is an aldehyde. So CH3, that's ethanol al, goes to ethanol, CH3, CH2OH. Okay. Have we decreased the amount of oxygen, bonds oxygen, or increased it? We had a double bond oxygen, now we have a single bond. So it's been reduced. Okay. We've added hydrogen across that carbonyl group. So ethanal, aldehyde, to an alcohol is reduction. You've added hydrogen. Okay, or lost oxygen. That's reduction. It's going to give all the answers before I can see it, but that's okay. I got to go through and fix this slide. 13.11. Let me do it so I can fix it for later on. 13.11. I think some others going to do the same thing. Benzoic acid to benzaldehyde. Going from a carboxylic acid and you have a benzene group, to benzaldehyde, to an aldehyde. Okay. Again, you've lost an OH group here, and it's replaced by hydrogen. So you've lost oxygen. You lost oxygen, that's reduction. Okay. Remember, oxidation is gaining oxygen or losing hydrogen. Reduction is gaining hydrogen or losing oxygen. Okay. Let me get some of those out of the way here. Cyclohexanone to cyclohexanol. Okay. An ONE ending means what?
Ketone.
Ketone, and goes to an alcohol. So a ketone is a carbonyl group. An alcohol is an OH. Okay. So you've added hydrogen, right? Across a double bond. So this is reduction. So cyclohexanone to cyclohexanol is reduction. You've added hydrogen across that double bond. Okay. Propanol to propanone. Again, this is your ketone, ONE ending, and OL is your alcohol. Okay. So we've lost hydrogen. We've gone from an OH group to a double bond, a carbonyl group. Okay, you've lost hydrogen. It's been oxidized. This is an oxidation reaction. Okay, you've increased the bonds to oxygen. You went from a single bond to a double bond. So you increase oxygen and you've lost hydrogen. Okay, so those are reduction and oxidation reactions. Okay, 2,3-butane-dione, which is in butter, to 2,3-butanediol. Okay, so dione, meaning there's two carbonyl groups, and it's a ketone, to diol, which is two OH groups. So again, you've gone from a ketone, in this case, there's two of them, to an alcohol. Okay, so has that lost or gained hydrogen? What's that one done? That doesn't have the answer there yet. So you got to come up with it on your own. So you've gone from a ketone to an alcohol. Is that oxidation or reduction?
Reduction.
It's reduction. You added hydrogen across that double bond. So it's reduction. You've added hydrogen. Perfect. And that's reduction and oxidation. Okay. Write a question for each of these reactions. Now we're going to go through each one and show the equation for them. So ethanol to ethanol. Okay. And basically you've added hydrogen, so plus H2. Okay. So ethanol to ethanol. And you've added hydrogen across the double bond. So this was a reduction reaction. You've added hydrogen. Okay. Benzoic acid to benzaldehyde. Okay. So here's benzoic acid. This is a carboxylic acid group here. We'll get into that next chapter. And this is your aldehyde. And this is your benzene ring. So benzaldehyde, benzoic acid. Okay. And this has gone from, have we added, what have we done to it? Have we increased or decreased the amount of oxygen? You decrease the amount of balanced oxygen, right? On the left-hand side, you have two oxygens. On the right-hand side, you only have one oxygen. So we've decreased the amount of oxygen. If you decrease the amount of oxygen, you have gone reduction. Remember the terminology. Oxidation is adding oxygen, losing hydrogen. Reduction is adding hydrogen or losing oxygen. And it's so much easier. It's just easy to look at organic chemistry and see whether the amount of oxygen has been reduced or increased, or not hydrogen has been increased. As we followed along organic chemistry, what is oxidation reduction? Cyclohexanone. Okay, here's our cyclohexanone. O and E ending is your ketone. Cyclohexanol. This is your alcohol. Okay. We have added hydrogen across this double bond, one to the OH group, one to the carbon here. So added the hydrogen here and the hydrogen to the OH group up here. So adding hydrogen was our reduction. Okay. To propanol to propanone. We had an alcohol to a ketone this time. Okay. So here's 2-propanol and 2-propanone or propanone. Okay. And you've released hydrogen. So we've lost hydrogen because we took here, hydrogen here, and that's formed this H2. And we've increased our bonds to oxygen. So we've increased oxygen and we've lost hydrogen. So what's that? Oxidation reduction. That's oxidation. Okay. We've lost hydrogen. 2,3-butane-dione or 2,3-butane-diol. Okay, again, there's 2 carbonyl groups, and we're using 2 hydrogens to go to each one of those. Okay, so you're adding hydrogen. You can add it to here, and here, and here, and here. You're adding it to the oxygen of each carbonyl group, and you're adding it to each carbon of the carbonyl group. So we're adding hydrogen. Adding hydrogen is reduction. Okay. The golden tan without fear of skin cancer. These are the spray-on tans that you can use. Okay. Self-tanning lotions become very popular in recent years. The result of a growing understanding of the link between exposure to the sun and skin cancer and to improvements in the quality of tans produced by these self-tanners. So I'm gonna give you this real orange looking tan. Some of the ones are pretty good now. The active ingredient in most self-tanners is dihydroxyacetone, DHA. So dihydroxyacetone, acetone has 3 carbons. Here's 2 OH groups and a carbonyl group. Okay. So it's an ONE ending, which means it is a ketone. Dihydroxy means there's 2 hydroxy groups. Okay. Now, how do we know that this functional group is a ketone and not an alcohol? When we're assigning functional groups, the most oxidized functional group wins. If there's 2 different functional groups, we choose the one that's the most oxidized, the one that has the more bonds to oxygen. The carbonyl group has double bond oxygen. The alcohols have 1. So the carbonyl group is the group that we named the functional group after. So this is an ONE ending rather than an OL ending. So we don't use OL because it's not as oxidized as the carbonyl group. That's how we decide. Because obviously there can be more than one functional group in a molecule, which there is right here. So we take the one that's the most oxidized, and that's the one that has this last ending right here. That's the one that determines the main functional group. So the most oxidized one wins out. Okay, so 1 carbonyl group, 2 alcohol groups. So it's dihydroxy, 2 OH groups, acetone, which is 3 carbons, and ONE ending is a ketone. That's DHA. Because it has both hydroxyl groups and a carbonyl group. DHA is a sugar. Okay, more precise, it's a keto sugar. It's a ketone sugar. And we get into a lot of sugars in chapter 17, I believe. We'll know how to name all these sugars and what they do in the body. This sugar is a byproduct of your own metabolism. We produce that. We produce it in the metabolic pathway called glycolysis, breaking down of glycogen to produce energy. When we eat glucose into our body, we take sugar in, it's stored, it produces glucose, so it uses energy. When there's extra glucose, we store it as glycogen. That gets stored in the body, our fat cells. We break down glycogen from our reserves to produce our energy. And in the process of breaking down, we produce DHA. A researcher by the name of Ella Winterstein discovered the tanning reaction while she was studying a human genetic disorder in children. Again, a lot of our discoveries are by mistakes. We just by accident. Okay. She wasn't going after a tanning product. Okay. Children, these children were unable to store glycogen, which is a polysaccharide, okay, or sugar polymer. That's, we link it together, make this long polymer, which is our major energy storage molecule in the liver. So some of these kids with this disease could not store glycogen. She was trying to treat the disease by feeding large doses of DHA to the children. Okay. Allows it to store in there and store glycogen that way. Sometimes the children spit up some of the sickening sweet solution, which ended up on their clothes and on their skin. And she noticed that the skin darkened at the spots where these spills and decided to investigate what was causing it. So the kids would throw it up, it get on their skin, and their skin would turn spots and become really dark, like a tan. DHA works because of the reaction between its carbonyl group and free amino group of several amino acids in the skin protein keratin. Remember, your skin has keratin in it, which is a strong fiber surface. Okay, it gives it its toughness, its thickness. Okay, amino groups have NH3 and they react with the carbonyl group of the DHA. The DHA produces brown colored compounds called melanoids when it bonds to the keratins. Okay. These polymeric melanoids are chemically linked to cells of the stratum corneum. Remember the stratum corneum? We haven't done it in this class, but the stratum corneum is the outermost layer of your skin. Okay, that's the dead layer of your skin that's on top. Okay, so that's what this DHA binds to, is the stratum corneum. It doesn't bind deeper than that. It binds to the outer layer of your skin, the stratum corneum. DHA does not penetrate the outer layer. So the chemical reaction that causes tanning only affects the stratum corneum, which is an advantage because stratum corneum is dead skin. It's not going to hurt anything. You're going to slough it off. And then you lose your tan too, by the way. Okay? So as the skin sloughs off, so does your tan. But it doesn't damage any of the cells underneath like ultraviolet radiation, like tanning boosts do. Okay? Tanning boosts go through the top layer and they tan down deeper. The tan lasts longer, but also causes skin cancers and destroys the layer of cells below the stratum corneum. Okay? Over the years, research has improved the quality of the tan that is produced. So early self-tanning lotions produce like that orange tan that everybody's famous for. So today's lotions are much more natural looking for tans. They've made improvements in it. DHA used today is a much purer form, and the other component of the lotion has been redesigned to a greater penetration. So it penetrates into the stratum corneum and holds the tan a little bit longer. Okay. Research has also taught us that tanning reactions work best at an acid pH. Okay. So newer formulas are buffered to a pH of 5, which is an acid pH. It adheres better to the stratum corneum and penetrates deeper in the stratum corneum to the keratin when it's an acidic pH. So we base that lotion as a pH of 5, which is acidic. So all these changes result in self-tanners that produce a longer lasting tan with a much natural golden color. Okay. And if you do it, you exfoliate before using a self-tanner. Think about why. You want to get the top dead layer off so it bonds better to the stratum corneum below that. Okay, so exfoliate, get the top layer off. That way your tan's going to last longer if you do that before you put the self-tanner on. Okay. Anywhere that the dead skin layer is thicker, there will be more keratin. You get a deeper tan. So when we begin with reactant, we often go get more products. The greater the amount of product in this case, the darker the color. So the more dead skin layer you have, the thicker it is, the darker the color is going to result from a spray on tan. Okay. Resulting tan often looks splotchy or streaky in cases where you have different amounts of reactant, okay, different layers. Okay. By gently removing some of the, was there a question? I thought I heard somebody. By gently removing some of the stratum corneum by gentle exfoliation, the surface of the skin and the tanning process becomes more uniform because you don't have that inconsistency anymore. And the tan becomes a much more natural tan. So again, another great adventure that's discovered by mistakes. Okay. Most recently, companies added a new sugar called ethrulose to the self-tanning lotions. And again, this is real similar. Here's your carbono group. Here's your 2 sugars for the DHA. And now they added this one. So they added another sugar to it. They added a third OH group. Okay. This makes the lotion much more penetrating. Okay. Erythrulose is a 4-carbon keto sugar that reacts exactly the same way as DHA. Okay. So now you get a better, more consistent tan with that one. Okay. Since they're different compounds, they produce different melanoids with slightly different properties, including color. Okay. So the tan produced by erythrolytes is less reddish in tones that's produced by DHA. It's more natural looking. Okay. While DHL tans develop in 2 to 6 hours, erythrolyte tans require 2 days to develop after you spray it on. Okay. It's penetrating down deeper. It takes a long time for those melanoids to develop. Okay. For this reason, erythrolyte is not used alone, but in combination with DHA. So use both together. The DHA gives you initial tan in 2 to 6 hours. And then the erythrolyte kicks in about 2 days later. Then it gives you a darker tan on top of that also. And the tans last longer that way. Okay. People often ask whether the tan from a bottle can protect against burns like a natural tan does. Natural tan darkens your skin and it's a protection against sunburn. Okay. The melanoids do absorb light at the same wavelengths absorbed by melanin, which is what gives you your tan. So you might expect some protection against the sunburn. Okay, but you don't. The protection is minimal. The SPF is only 2 or 3 protection from the spray-on tans. So a spray-on tan will not protect you against sunburn. Whereas a natural tan will. Okay. So self-tanners offer an excellent substitute to a suntan. They produce the same golden tan without the danger of overexposure to the sun's harmful ultraviolet rays and the skin cancers that develop from that. Addition reactions. Principal reactions, the addition reaction across the polar carbon double bond oxygen bond, the carbonyl double bond. That's where we've been adding hydrogen to it. Okay. It's very similar to addition hydrogenation reactions of alkenes when there's a carbon-carbon double bond. Same thing. We took a alkene and made it into alkane by addition reactions of hydrogenation when there's a double bonded carbon. Requires catalytic acid in solution. The product of the reaction is a hemiacetal. Now these are going to become real important in biochemistry. We're going to have hemiacetals, acetals, hemiketols, and ketols. And we're going to form them by addition reactions across the carbon oxygen double bond. Okay. This is a hemiacetal right here. You have an R group and an H group. Okay. Attached to that carbon, you have an OH and an OR. So you have 2 oxygens bonded to that carbon. One has a hydrogen, one has an R group. If this is an R and an H, it's an acetal. If this is an R and R, it's a ketal. If there's an OH here, it's a hemi, which means it's halfway reacted. We reacted with addition reaction to produce our OR group. Okay. If we react the second time, we're going to get rid of that OH and make that an OR. That's going to make it an acetal. So this is what a hemiacetal looks like. Okay, that's your hemiacetal group right here. RH are your backbone, and we added OR and OH. Okay, whenever we have an OH and the OR, it's going to be a hemi. If it's an R and H, it's a hemiacetal. If it's an R and R, it's a hemiketal. Okay, hemiacetals are very reactive. They undergo substitution reactions where the OH group of the hemiacetal is replaced by the OR group of the alcohol. Okay, so it's a 3-step reaction, and it's going to be at equilibrium, so let's go both directions. Okay, the final product is going to be an acetal, where this OH is replaced by an OR. And then that's going to be an acetal group. And again, we're going to use these in biochemistry. Wrong button there. This reaction is reversible, which means it comes to equilibrium. It reacts forward and backwards. So we're going to have a starting point. We're going to have a middle product. The middle product is our hemiacetal or hemiketal. Then we have a final product, which is our acetal or ketal. Okay, and the reaction goes in both directions. Okay, so this is what it looks like. Okay, this is what we have. We're going to react an aldehyde with an alcohol. Addition reaction. Okay, we're going to take the hydrogen and it's going to react to the oxygen, and the OR is going to attach to the carbon, just like hydrogen did. So now we got two different things here. It's the same principles as hydrogenation, except we're using an alcohol. Okay, so this double bond opens up right here. Okay, and we add the hydrogen goes to the oxygen to give you OH. And then instead of having a hydrogen, we have OR left over, right? We don't have a hydrogen anymore. We have OR, and that bonds to this carbon. So here's our OR from our alcohol, and here's our hydrogen from there. So this is an R and an H, and you still have an OH group here, so that's a hemi, and it's an acetal. So it's a hemiacetal. And this reaction is reversible, shown by the double arrows here. Now, this reaction continues to go. Reacts with a second alcohol, which is the same alcohol we had over here. Okay, same alcohol. Reacts with a second molecule of the alcohol, because hemiacetals are very reactive. Okay. Then we take the OH group. Okay, so we have our H here. The hydrogen reacts with the OH group here to give you water, and this OR attaches to that carbon. So the OH is removed with hydrogen from here to give you water. Water is a very stable component. And then the OR group attaches here to give you an OR here and our OR here. Okay. So you have two OR groups, an R group, and a hydrogen. That's an acetal. If this hydrogen here was a R group, then it would be a ketal. So like I said, these are probably things you've never heard of before, and it's going to be a little confusing first. We'll go through a bunch of examples and work it out. But you have to learn the terms. And you got to know the terms for your final and for your midterm. Hemiacetal, acetal. Hemiketal, ketal. And know the difference. Hemiacetals and hemiketals are very unstable. They're the intermediate group. And this reaction goes both ways. Reaction goes back that way, and reaction goes back that way. So it comes to equilibrium at a certain point. Okay, reactions are reversible, all the reactions in this. And all it is an aldehyde or a ketone that's going to react with an alcohol. Then it's going to form this hemiacetal or hemiketal, and it's react with the second alcohol molecule. Okay? Now that everybody's thoroughly confused, we'll do some examples and hope that'll straighten it out. But you need to learn the key words: hemiacetal, acetal, hemiketal, and ketal, and know what they look like. Okay, so we have an aldehyde reacts with our alcohol to form a hemiacetal. Hemiacetal can now go back and form the alcohol in the aldehyde, or it can go forward. Another reaction reacts with another alcohol, the same alcohol, to form an acetal. Okay, so hemiacetal and acetal formations. Okay, aldehyde or ketone, alcohol forms a hemiacetal or hemiacetal. Okay, again, you have your R group and your R2 group, your OR and your OH. If R2 is hydrogen, that's a hemiacetal group. So in this case, R2 is hydrogen. If R2 was a R group or a carbon group, then that would be a hemiketal. Okay, then it reacts with a second alcohol to form your acetal group. Acetal, here's your R groups, and now you have two OR groups. Again, if there's one OR and one OH, it's a hemi. It's halfway there. If there's two OR groups, then it's a acetal or a ketal. Okay? And you're always forming water as your byproduct be pulled off of there. So this is a general structure of a hemiacetal, as long as that's a hydrogen. Okay, as long as that R group is a hydrogen, that's a hemiacetal group. Okay. Again, if R2 is I don't know why they put R, they should just put hydrogen. I'll have to change that too. I don't like how it does that. It's kind of confusing to look at, but if that R2 is an H group, this is a hemiacetal. This is a acetyl group. Okay. You have an R and an H. That's your acetyl. If one's an OR, one's an OH, it's a hemi. You have an R and an H. Again, that's your acetyl group. If they're both ORs, then it's an acetyl. It's only hemi when one of the ORs is an OH because it's halfway there. It's not through the whole structure yet. Okay, so that's the basics for what we're going to be doing. Okay, we'll go over a bunch of reactions and hopefully make a little more sense. I know it's confusing. Just kind of hang in there and work with me, and we'll get through this because it's going to be real important when we get into processing sugars in the human body and biochemistry. So addition reactions will also occur between a ketone and an alcohol. That was an aldehyde in an alcohol. Now we got a ketone in an alcohol. That's going to give us our ketones. In this case, a more reactive intermediate is called a hemiketal, and the product is called a ketal. Hemiketal means there's an OH and an OR. Keto means there's an OR and an OR. Okay, and then two R groups attached. Okay, that's the difference. Whenever you have an OH, you're in the process, you're in the middle. So it's hemi. The general equation for a keto formation is, now we got a ketone. Okay, both those R groups are carbon compounds, carbon groups. There's your alcohol. Okay, and it's an addition reaction. We're going to add H and OR. We're going to add H to the oxygen. We're going to add OR to this carbon. So here's your OR. Here's your OH. And we still got our backbone, our two R groups from the ketone. Okay. So this is a hemi because it has an OH group still, not two ORs, but an OH group. So if it's an OR and OH, it's a hemi. And we have two carbons attached, one on each end. So it's a ketal. So that's a hemiketal. Everybody get the first step. Any questions on that? Someone give me a nod or a yes or a thumbs up if they understand the first step.
Yes.
Yeah, okay, perfect. Okay, second step, we have this hemiketal, the very reactive. It can either go back to where it came from, forming a ketone and an alcohol again, or it can proceed on the other direction where it adds to another alcohol that's in solution. Okay, the other how now this is a little trickier reaction because what it does is it takes off water as a product. Water is very stable. So again, we're going to break this here. Okay, this hydrogen is going to attach to this OH group, and that's going to form this water. So it pulls that off, and what's left is this OR group here. And this OR group attaches to the carbon when the OH group is pulled off. Okay, so we formed our water, and now we've got an OR group that's formed, and our OR group that was originally there, and these two R's. Okay, so this is not a hemi anymore because there's two ORs. There's no OH. There's no hydroxyl group. There's two OR groups. So now it is a ketone because there's two carbons, one attached to each side. Okay, so it's a hemi if there's an OH group present because it hasn't gone on its full reaction yet. That's what's called hemi. Okay, and then keto because there's two R's attached to the carbon. Then once the second alcohol reacts, it becomes a ketal. So hemiacetal, acetyl, hemiketal, ketal. Okay, so there's your ketone, there's your alcohol, and then it forms a hemiketal. Okay, hemiketal reacts with another alcohol in solution, the same alcohol that's floating around. So, I mean, this alcohol here, this alcohol right here is the same thing as this alcohol here. It's in solution. It's just reacting with it. And it forms a ketal for the next step of the reaction. Okay, so it's 2 steps. Okay, when you're forming an aldehyde or a ketone, it's going to react with an alcohol. It's going to form a hemiacetal or a hemiketal. Okay? Then those are going to react with another molecule to form either a acetyl or a ketal. All right, so a ketal is a final product in the reaction between propanone and ethanol. The hemiketal is formed as an intermediate step. So let's go through that reaction. You've got propanone. We should all know how to draw these by now. Propanone is carbon, 3 carbons, and it's a ketone, so it's a carbonyl group. There's propanone, and we're going to react a ketone with an alcohol, CH3, CH2OH. Okay, it's a 2-step reaction. Okay, so here's our CH3. We'll draw this out, CH3, CH3. And again, it's an addition reaction, just like hydrogen, except now we're adding a hydrogen to our oxygen and then this thing. So these are 2 parts, writing part 1 and part 2. That's where we're adding across that double bond. So here's our bond with oxygen. That's opened up, right? So still the same thing. So now we're adding hydrogen and we're adding O, CH2, CH3. Okay. Everybody with me so far? That's an addition reaction across the carbonyl group, hydrogen, and then the OCH2, CH3. We're just like we split hydrogen in half, we're splitting this in half now. Okay. Okay, and then this one, we just do a reaction this direction here, is going to react with another alcohol. So plus CH3, CH2OH, another alcohol. Okay, same alcohols over here, but now we're going to divide it again. Okay, this H and this side. Now this hydrogen here, okay, is going to react with this OH group right here to form water. This hydrogen comes up here and plucks it off, leaving water. That leaves this one to attack to that carbon because the OH is now gone. So then we have CH3 bonded to carbon, bonded to CH3, bonded to, and again, this was our alcohol from before, CH2, CH3. Okay, that's exactly what we got. And now we just remove the OH from the top. And now we're going to add this part right here, O, CH2, CH3. There's our alcohol. That's the reaction. That's how it occurs. That's why it, oh, plus 1, I'm sorry. Plus, go back to red, H2O. You're pulling that off and adding that. Okay, so this is a ketone. This is an alcohol. This, okay, what is that called?
Hemiketal.
Perfect, perfect. It's a hemiketal. Ketal because this carbon and this carbon are attached to the carbon with the oxygen attached. So you have the carbon on each side of it. Okay, and it's a hemi because it still has this OH group right here. That makes it a hemi. And then a ketal because it has one alcohol already attached. So it's a hemiketal. And then we produce water, and this final product is a ketal because it adds with a second alcohol right here. Okay. So we take a hemiketal, add it with another molecule of alcohol. Okay, the OH comes off, combines with the H from the alcohol, forms water. Then the rest of that alcohol, this portion right here, this remaining portion, attaches to where the OH group was onto that carbon. and it forms a ketone. And that's how they react. So now you know acetyl, hemiacetyl, ketyl, hemiketyl. Propanone, our ketone. We are adding an alcohol in the presence of acid. And these double arrows mean it's reversible, both steps in the reaction. It goes both directions, goes forward and backwards. Okay, so the first step of the reaction between a ketone and an alcohol is to form a hemiketyl. Okay, there's two carbons attached, each side of the carbon. Here's your OH group. Remember, we opened up that double bond and we added an H to the oxygen, and then the remaining was the O, CH2, CH3. Okay, just like hydrogenation, except now we're adding a hydrogen and an O, CH2, CH3 rather than another hydrogen. Okay, and then we add a second alcohol. Similar reaction, we produce water and we produce our ketone. Here's your two OR groups, and there's your two carbons. Right? That's how the reaction occurs. So that's propanone, that's your ketone. Ethanol, that's your alcohol. And it forms a hemiketyl. Reacts with another molecule of alcohol, and it forms a ketyl. All right. I know it's kind of confusing. And I know when you're watching me do it, you can follow along. When you sit down and do this on your own, it's going to be a little more complicated. If you have a question with it, let me know. But does that at least make sense how we're going through this process now?
Yes.
All right, thank you. All right, so formation of hemiacetyl and hemiketyl. So products of the addition reaction between an aldehyde and an alcohol is a hemiacetyl. Okay. Okay. So here's your aldehyde. Here's your alcohol. The first step is to add across this double bond. So just think of it as two hydrogens, except the one hydrogen being placed with an OR group. So the hydrogen attacks the oxygen here. This double bond opens up just like it did before. And now you got that opening on that carbon. So this portion here attaches to the carbon. So you get an O, CH3, because you had methanol as your alcohol, and you still get all this the same. This group stays the same right here. That never changes. That's your core right there. That's your aldehyde. So now we've got an O, CH3 added, and we've got an H added. So now we have OH and OCH3. So this is a hemiacetyl. Okay, hemi because the OH group is still here, and acetyl because one of the attachments to the carbon is a hydrogen. You have carbon has one line, it's carbon another. So that's a hemiacetyl. Okay. The product of addition reaction between a ketone and an alcohol is a hemiketyl. So I said before, if it's an aldehyde and an alcohol, it's going to form a hemiacetyl, then an acetyl group, acetyl. If it is a ketone and an alcohol, it's going to form a hemiketyl, then a ketyl. Okay. So here's your ketone. Okay. And this core is going to be the same core. That's not going to change. The only thing that's going to change is we're going to open up this double bond like we usually do. And this hydrogen is going to attack here. And this OCH3 group, the rest of it, is going to attach to the other end of the double bond. And this is going to be a hemi because it still has an OH group here. And it's going to be a ketyl because there's two R groups attached to it. Okay, so hemiacetyl or hemiketyl carbons are made up from two functional groups. Okay, we have alcohols and ethers. And this creates a special functional group. Okay. So here's your alcohol. Okay. And here's your ether. Remember, ether is ROR. Alcohols are ROH. So this is an ether because here's your R group, an O, another R group. So this is an ether, and this is an alcohol. So you have two functional groups making those up. Now we got this, so you're going to name hemiacetal and hemiketal groups. Okay. Let's move some of these out of the way so you can see what we're pointing at. Okay. So you look at that carbon. Okay. And you can see, okay, there's an OH group here. There's an OR group here. So here's your ether, and here's your alcohol. Okay. So recognizing hemiacetals, acetals, hemiketals, and ketals. All right. This sums up what the recognition of what we've been doing here. So here's your carbon we're bonded to, the center carbon. If we add two alkyl groups, we have an R and an R. Okay, that's going to give us keto groups. Okay, because here's our two R's again. If we have two ORs attached, that is a ketal. Okay, again, here's our two R's. If we have an OH and an OR, this is a hemi ketal because we have that OH group still attached. If we have an R and an H, here's our R, here's our H. We have an OH and an OR. Again, the H is there, so it's a hemi, just like both of them. And that's an acetyl group, hemiacetal. Okay, here's our R and our H again. Now we got two ORs attached to it. Okay, now that's our acetyl. Okay, that's how it breaks down. So an aldehyde and an alcohol is going to give you a hemiacetal and an acetyl. A ketone and alcohols going to give you a hemiketal and a ketal. So everybody's going to tell the difference between an acetyl, hemiacetal, keto, and hemiketal. So you'll know the difference, be able to tell those on an exam. I'll get some of those words out of the way here again. So there's your hemiacetal. Okay. And there is your acetyl. Okay. Then your keto and your hemiketal. Okay. Identify each of the following structures as a hemiacetal, acetyl, hemiketal, or ketal. Okay, what is that?
Hemiacetal.
Perfect. That's a hemiacetal group. It's hemi because your OH is still there, and it's acetyl because there's an H and an R group. So hemiacetal. What is that one?
Keto.
Ketal. Perfect. Again, two R groups and OR is attached to them. Okay. What is that one?
Acetyl.
It's an acetyl group, two OR groups, and an R and an H. And one more. What is that one?
Hemiketal.
Hemiketal. Perfect. You guys got this down pat. It's a lot quicker than the other classes used to go. You take a long time to understand these concepts. That's really good. So again, acetyl, hemiacetal, keto, hemiketal. You guys know the differences here. All right, one more try with these. This one is a what?
Hemiacetal.
Hemiacetal. Got it. This one is
Hemaketo.
hemaketo. Perfect. And this one,
Acetyl.
acetyl. Perfect. And this one here,
Keto.
keto. Got it. Perfect. Any questions on those? Now we're gonna make it a little bit harder. Okay. They can, if they're, was that?
No.
Got to make it challenging. All right. So the aldehyde and the alcohol functional groups can be part of the same molecule. It doesn't have to be separate parts. So it can wrap around and form cyclical structures. Okay. So if you have an aldehyde end and you have an alcohol end on the same one, it can reach around and form that same structure in a ring structure now. Okay. So the carbon can attack, switch off the oxygen, so you can form a cyclic hemiacetyl group. Again, so here's your H, here's your OH, here's your OR, and here's your R. Okay, so that's a hemiacetyl group because you have a hydrogen. The hydrogen's up here. It's a hemi because you still have your OH group attached here. And then your one OR group and one R group. Okay. So if you look at this thing, it would be the compound here is 4-hydroxy. Again, there's your hydroxy group, pentanal. Remember when your function group is an aldehyde, and the hydroxy is because the alcohol is not your function group anymore. Remember, if there's two functional groups, it is the most oxidized that takes precedence. So that's an aldehyde. So it's 4-hydroxy heptanol, and it can wrap around just like before and form, okay, a cyclical now hemiacetyl. And that's what's going to happen with your sugar groups. When we're dealing with sugars in biochemistry, we're going to do all these hemiacetyl groups, and they're going to form ring structures. Okay, and that's going to form your sugars, and that's going to do a lot within biochemistry. So hemiacetyls and hemiketones forming intermolecular reactions are unstable and can continually form acetyls and ketones, just like was done before, same reaction.
I'm sorry, can you repeat what you said? You said whoever has the most oxygen in the aldehyde group takes precedent?
Right. If you have a compound that has an OH group and an aldehyde or a ketone group, the group that has that is the most oxidized becomes the one that you name it after, takes precedence. So if there's two functional groups, the most oxidized one wins out when you're naming it. Does that make sense? Okay.
Yeah.
Okay, cool. So with intermolecular forces involving 5 or 6 carbon rings, then you form sugars, and that forms a stable compound. So it doesn't proceed back onto an as acetyl or ketone or keto, sorry. Okay, so these reactions, the cyclical ring form, okay, is more stable than the linear form. And we're gonna start writing linear forms and ring structures with our sugars as we get into biochemistry because they're extremely reactive. Okay, so here, these are Fischer, this is what's called a Fischer projection, and this is the ring structure, okay? But it's binding upon itself because here is an alcohol and here is an aldehyde. So we're getting that same reaction. It's just within the molecule now to form a hemiacetyl or a hemiketo, depending on what the top group is, whether it's a ketosis or an acetylosis, the aldehyde, which is aldehyde or ketone. So then this folds over, okay, and it's going to form a ring structure. Okay, so here's your carbon. This is where the carbonyl carbon was, right here. There's your carbonyl carbon. Okay, so to attach to that carbon, we have an H, we have an OH, we have an OR, and we have an R group carbon. Okay, so attached to that, where that red carbon is, that real spot, that carbon has, so here's your carbon. It has an H, an OH, an OR, and a R group. Okay, so that's really familiar now. Here's your R and your H, and your OR and OH. So it's a hemi, okay, acetyl. Okay, it just looks different because it's in a ring structure. And you notice the only difference between the two formed is this one here, the H is on top and OH is down. This one here, the OH is up, the H is down. This is beta, and that's alpha. Because when the ring forms and the ring closes upon itself, half the time the O is going to go up, half the time it's going to go down. So to form an alpha or beta for the sugar group. Okay. So we're forming these sugars from these linear structures. Okay, it's going to form a hemiacetal if this is a aldehyde, and it's going to form a hemiketal if this is a ketone. Okay, so this is D-glucose, which is our main form of energy for the brain and for most of the rest of the body. Okay, this was called an open chain. Open chain sugars are very unstable. You don't need to have OH groups hanging out there. Okay, this is your alpha D-glucose. Let's see if we can get, sometimes all these red marks get in the way. Be easier if you can see it a little bit here. Okay, so here's your alpha D-glucose, which is the top one. Again, when the OH is down, it's alpha. When the OH is up, it's beta. So this is your alpha D-glucose, and the next one's going to be your beta D-glucose. Okay, so open chain structures of sugars are very unstable. They fold over upon themselves. Again, so here's your aldehyde group, and here's your alcohol. Okay, and they're going to form upon themselves, and they're going to form that ring structure. And the ring structures are hemi. In this case, it's an acetyl group because this is an aldehyde right here. Okay. So when the hemiacetal or hemiketal of one monosaccharide reacts with a hydroxyl group of another monosaccharide, the product is an acetyl or a ketyl. So now when these attach to each other, now we form an acetyl group or a ketyl group. So a sugar molecule is two monosaccharides. So each of those combined, and it's called a disaccharide when two monosaccharides come together. Okay. So the carbon-oxygen-carbon bond between the two monosaccharides is what's called a glycosidic bond. So when these two link together, so here's your two separate ones. This is one here, and this is the other. Okay. When these two link together, this bond, okay, now you've got an OR bond now. No more OH in between there. So these are ketones or acetyl groups. Okay, and your byproduct was water because that's what you pulled off between them. Just like we did before, same type of reaction, except now you're using a ring structure to do it. Okay, and this bond here is what's called a glycosidic bond, which links two sugar molecules together. In this case, it's a 5-carbon ring, and then a 6-carbon ring. Okay, so this is alpha glucose, and this is beta fructose. Okay, and those link together, and it forms sucrose. Sucrose is table sugar, as we put in everything. Okay. So you got a 6-carbon sugar and a 5-carbon sugar, and they're linking together through a glycosidic bond. And it's the same reaction we've been doing. These are both hemiacetals, okay? Hemiacetals, and they link together to form an acetyl group. Okay, that's your glycosidic bond that does it. Okay, because here's your H and your OH. This is where you're going to link right here. This is what's going to form your water. Okay. Your high OH and your H link together. Okay. And it pulls off water. And this forms a bond between the oxygen that's left between those two. Okay. Everybody see where the water, how the water's coming out from there? So if I take, so this hydrogen and this OH becomes this water right here. This oxygen here that's left over, this completes the bond between these two. So you come down from here and you form your oxygen and you form your oxygen between these two carbon atoms. There's your oxygen bond. Okay, that's your glycosidic bond. Next, we go into keto-enol tautomers, which are isomers. Keto is the carbonyl group. Enol is the carbon double bond with an OH group. So E and E was a double bond, remember? OL is an alcohol. And it's going to flip-flop between those two forms. Is basically what that is. So let me just check, make sure everything's still recording and doing good. Yep. Okay, perfect. So tautomers are isomers which differ in placement. Okay, they differ in placement of a hydrogen atom because one's going to bond to the oxygen now to form an alcohol group, and they differ with a double bond between two carbon atoms. So the double bond is going to be between a carbon and oxygen or between two carbon atoms. So it's going to switch, and the hydrogen is going to move from one place to another to form an OH group. Okay, so the keto form has a carbon double bond to oxygen. Oh, that's my pen. Okay, so it has a carbonyl group. Okay, the enol form has a carbon-carbon double bond. Remember, E and E was a double bond. There's your enol form. Okay, so the keto form has a carbonyl group. The enol form has a carbon-carbon double bond. Okay, the keto form is usually the most stable. Well, with the carbonyl group. Okay, so here's what we're looking at. Here's our carbonyl group. Okay, if we take a hydrogen off what's called the alpha carbon, which is the carbon adjacent to the carbon of the carbonyl group, this hydrogen moves over here, and this double bond flops down. So now you formed an OH group and a carbon-carbon double bond. Okay, so we've only moved the position of the carbon-carbon double bond and a hydrogen. That's what we've changed. Okay, so that's your tautomer. Okay, it's when the bond comes down, you form the new carbon-carbon double bond, and now you got an OH group. This is the keto form. So this is keto because it's a ketone, and this is an enol form because it's an E and it's an OL, an alcohol group. Okay, that's all it is. It's same number of molecules, same elements in each one. But when hydrogen is moved and the carbonyl group has now become a carbon-carbon double bond. Okay, so this is your keto, this is your enol. Okay, using a real example now. This is ethanol. Okay, again, for the keto form, you're going to have this hydrogen, the hydrogen on the adjacent carbon to the carbonyl group. Transfer this oxygen and it slams this double bond here between these two carbons and it forms this carbon-carbon double bond, and now you have an OH group. Again, that's your keto form, that's your enol form. Those are keto-enol tautomers. Okay. Looking at the same thing here. Again, this is the carbonyl group. This is used in most stable form. Okay, this is your keto. Okay, this hydrogen transfers that oxygen, and this bond here. Oops. The hydrogen moves over to that oxygen, and this double bond swings down to form the double bond in between there. Okay, and that forms this carbon-carbon double bond and an OH. This is your enol form. Okay. So the keto form has a structure typical of an aldehyde or a ketone. If this R group right here, if this is an H, it's an aldehyde. If it's an R group, if it's a carbon group, it's a ketone. Okay. The other form is called the enol form. So this is keto, this is enol. Okay. The enol form has a structure containing a carbon-carbon double bond, which you can see right there. Okay. And a hydroxyl group, which is your OH group right here. Okay. The functional group for this is an alcohol. Okay. The functional group for this one here is a ketone or an aldehyde. Okay. So the R groups are either alkyl groups, which are carbon, or they're hydrogen groups. All right, so draw the keto form of ethanol and write an equation representing the equilibrium between the keto and enol forms of this molecule. So first of all, what's ethanol? Where are we? Oh, ethanol right there. Okay, we're looking for ethanol. So ethane is 2 carbons, single bonds. Al is aldehyde. So it's ethanol is CH3, C double bond O, H. Okay, that's ethanol. Okay, that's the keto form, right? The enol form, you're going to have still carbon here. You can take one of these hydrogens, move it to that oxygen, and that carbon-carbon bond is going to sling down. Maybe take a hydrogen from the adjacent carbon of the carbonyl group. It attaches to the OH, and then this bond slings down to here. So there's your CH, 2 CO1A, COH, and then CH. Okay, so that's ethanol, this alcohol here. So you produce ethanol is the other form, the enol form. This is the keto form, okay, which is ethanol. This is an enol form, which is ethanol, the primary alcohol. Ethanol, I'm sorry. It should be an E because double bond there. Okay. Don't forget to include that in that's where the enol comes from, the name. So this is ketone, this is your enol form. All right. So ethanol, 2 carbons. Here's your carbonyl group. You can see it clear here. You can take this hydrogen, or any of the 3 hydrogens, just the same. This hydrogen moves over and attacks that oxygen, kicks those electrons from that bond into this double bond here. So it creates a double bond between these 2 carbons and an OH group. Again, this is your keto form, which is ethanol. And this is your enol form, which is ethenol. Okay, double bond, EN, OL ending for the alcohol, number 1 position. Okay, draw the ketone enol forms of propanol. Propanol is 3 carbons. Al ending is an aldehyde, right? Okay, so propanol is CH3, CH2, C double bond O, H. Okay, and this is the keto form. The enol form, we take one of these hydrogens, attach to that double bond, and that other bond slings down between the 2 carbons. So we have CH3, bonded to C, bonded to H, double bond, bonded to C, bonded to OH, bonded to H. Okay. And this is your eno form. And this is propene ol, 1-propanol. Right now, since the double bond is here, you can see this hydrogen's relationship. This is cis. The way I drew it is cis 1-propanol. Right. Is that kind of making sense, everybody?
Kind of.
Kind of. Okay. I know there's a lot of material in the last part of this chapter, a whole lot of new material. Okay. But we'll go through a couple more examples here. So just got to remember identify your carbonyl group. That's your keto form. Once you do that, you find your adjacent carbon and you take one of those hydrogens and it's going to attack that oxygen to form an OH group. And that double bond is going to move down, okay, to form the double bond between the two carbon atoms now. So you get CH3, CH, double bond, COHH. Okay, again, this is your keto form. This is your enol form. Remember, En is a double bond, OL is an alcohol. 3-pentanone. 3-pentanone is CH3, CH2, C, double bond oxygen, CH2, CH3. 5 carbons. ONE is a ketone, and it's at the number 3 position. Okay, this is a keto form. The enol form would be CH3, CH. We're going to take one of those H's now. One of these H's is going to come, attack this, and drop the double bond between the carbon atoms. Okay, so you have your hydrogen attack there. Your double bond now forms there. CH2, CH3. Okay, and this is your enol form. Now, what would happen if instead of this hydrogen, we use this one? And the double bond went between these two carbons here. Same thing, right? It's completely symmetrical. If I put the double bond on the other side, which very well could be, we could have used the other carbon, lost its hydrogen from the double bond, could have gone there, but it's the same thing. It's symmetrical. It's the exact same compound. This is called 3. And this is pentanol, ENE double bond, OL alcohol, 5 carbons. The OL group's in number 3 position. If we would have done, if this double bond would have been over here, it would still been the same thing. Okay. I think I'm missing something here for some reason. I'm not telling you what the double bond is. So the actual name of this would be pentanol. The double bond's at number 2 carbon, right? Yeah. So it would be 2-pentene 3-ol. I forgot, I'm sorry about that. The double bond is at the number 2 position, the ENE, and then the OL is at the number 3 position. It would be the same either way, whichever way it folded over. So I'll show you that. Okay. So we could use this hydrogen here or this hydrogen here. No matter which one we use, it's going to form the exact same compound because it's symmetrical. The hydrogen comes up, attaches that oxygen, double bond comes down. Could have done the exact same on the other side, you still get the exact same product. Okay, so it's pentanol. The OH group is at number 3. The double bond is at number 2. So 2-pentene 3-ol. Okay. Okay, phosphoenolpyruvate is a biologically important enol we're going to use. We'll be talking about that one. Okay. A high energy bond phosphorylate compound in living systems. This is what forms ATP. That should be familiar to a lot of people. This is your high energy phosphate bond. That's what produces energy in biological systems. Allow muscles to contract, allow everything else to happen. Okay. Phosphoenolpyruvate is produced in the next to last step in the metabolic pathway called glycolysis. Okay, the breaking down of glucose to produce ATP. We break down glucose to give us energy to make more ATP. Okay, which is the first stage of carbohydrate breakdown. We start to break those down. Okay. In the final reaction of glycolysis, the phosphoryl group from phosphoenolpyruvate is transferred to adenosine diphosphate. So you've taken ADP, adenosine diphosphate, and you created ATP by adding that phosphorylated phosphate group to it. Okay. The reaction produces ATP, which is a major currency of all cells. So we're going to use an enol compound to do that. Phosphoenolpyruvate. Okay, here's your enol compound, your double bonded carbon. Okay, and this is your phosphate group that adds to it. And that adds right to the carbon. Okay, you'll have 3 of those phosphate groups for ATP when you add to a diphosphate one. Okay. All right, so now we have aldol condensation. Okay, these are self-addition or condensation reactions. Okay, means use 2 molecules of the same aldehyde or ketone, and they condense into each other and form a new compound. The alpha carbon, remember alpha carbon is a carbon adjacent to the carbonyl carbon. So the alpha carbon of the second molecule adds to the carbonyl carbon of the first molecule. Now these are going to be confusing again at first, but they'll make sense as we go through it. Okay. You need a strong base to catalyze the reaction, like hydroxide. They're real complex reactions. I'll show a simple way to show how molecules, how they're moving around, but it's a real complex actual mechanism for these things. All right, so this is what's going to happen, believe it or not. Okay, you have 2 ketones or 2 aldehydes, and they're to condense into one. Okay, so what happens, okay, is this double bond here is going to open up. This double bond right there opens up, brings electrons up. And let me see how I'm going to explain this to you the right way here. Okay, the hydrogen from the alpha carbon, which is the carbon adjacent to your carbonyl group right here. The hydrogen from that, follow that blue line, attaches to this OH group, attaches the oxygen. Okay. So you get an OH group up there, and then you get your R, CH2, CR2, OH. That's this portion right here. If you follow that, all we've done is run 1 hydrogen up to this OH group. Okay. And now you've got an open carbon right here, an open area right there. Okay, so we've taken the set, let's call this the second one. Okay, the one below it. We've taken the H group from the alpha carbon, brought it up, attached to the oxygen of the carbonyl group to form an OH group. That leaves this carbon open right here for another bond, because that only leaves 3 bonds now. Okay, so what attaches to it is where you've taken this group off. This carbon now is missing a bond also. So this carbon attaches to the carbonyl carbon. That's what the reaction is. I know it's a real complex set of mechanisms, and it's kind of hard to think about at first. But the easiest way to do it is to line them up just like we did here and say the alpha carbon. Remember, alpha carbon is the one adjacent to the carbonyl group. Loses a hydrogen, and it comes up to this oxygen right here. That leaves this open with a bond. That leaves this carbon open with a bond. Okay, in other words, this carbon here only has 3, and this carbon here only has 3. So they attach to each other to give each carbon 4 bonds. And that's where the attachment is. So if you look at your main group, the main group here is this right here. Okay, the OH is where the hydrogen is attached. Now this alpha carbon attaches to that carbon right here. And this is the same group here as is right here. Okay, just the hydrogen is gone. So that's his CH. Okay, everybody thoroughly confused now.
Yep.
Okay. It does it. These condensation reactions are really tricky. But what you got to remember, most students forget that's the alpha carbon. It's the carbon adjacent to the carbonyl bond that's going to lose a hydrogen. And therefore, that's where it's going to bond. That's all it does. This carbon, their alpha carbon, this carbon loses a hydrogen and bonds to where the carbonyl group is. That's it. That's the whole thing. It looks a lot harder, but that's all it does. It loses a hydrogen, creates an OH, and then where it lost the hydrogen, it bonds to the carbon where it created the single bond from the double bond. So this is called an aldol. Okay, it's an aldehyde and an alcohol. So it's an aldol. These are alcohol condensations because it's condensing into itself. Okay, so the net result of the reaction is the carbonyl group of 1. We're going to call this one number 1, this one number 2, just for fun. Okay, the carbonyl group of number 1 accepts a hydrogen from the alpha carbon of number 2. That's the important step. Okay, so the carbonyl group of 1 accepts the hydrogen from the alpha carbon of 2. Okay, that's where this carbon went up and attached to the carbonyl group to give you this OH group on top. Then the carbon with the OH group attaches bonds to the alpha carbon of number 2. So where it lost its hydrogen, it bonds to the carbonyl carbon. All right. So let's do one. The aldol has an OH beta to the carbonyl group. Okay. So in the aldol, this is your aldol. Okay, this side here, this is your aldol. It has a OH group beta to the carbonyl group. Remember, carbons are numbered by Greek letters, where the carbonyl group is the grouping. Then you have alpha, beta, gamma, delta, epsilon, etc. All the Greek letters. Okay, so this is your beta carbon right here. And that's the one that has the OH group attached. So the aldol has an OH group beta to the carbonyl group. There's a carbonyl group. So it's on the beta carbon of the OH group for an aldol. Okay, so if we look at this compound, let's break this apart. All right, so let's take it step by step. HCH, C double bond O, bonded to H. Okay, we're going to use the same compound for self-addition reaction or condensation reaction. All right, so we got an H, C, H, C, O, H. All I do is write that twice. Now, this is number 1. This is number 2. Doesn't matter which one's which. This is when you keep track of it. So the first step is identify the alpha carbon. Okay, here's your carbonyl group. This is your alpha carbon right here. We're going to take this hydrogen, doesn't matter which one it is, and this is going to attack and attach to the carbonyl group there. So far, so good? If we can get that step, the rest is pretty straightforward. We got it?
Yep.
Okay, perfect. Okay. Just got to remember it's the alpha carbon. Now we got an OH formed up here, and this bond swings down here to make this ready. So now this carbon here and this carbon here, I'll put different colors here. So this carbon and this carbon only have 3 bonds attached. So they're going to attach to each other. So they're going to form a connection. So it's going to be H, C, H, just like that. And then this carbon is going to have an OH, and this carbon has a hydrogen, and this bond drops down, and it connects to the C double bond OH. All I did was drop this line right here. I dropped that bond between them. Everybody see it? I just took the number 2 and slid it over and connected to the carbonyl carbon, or what was the carbonyl carbon. So now each carbon has 4 bonds. And that's it. Then we just straighten out when we write it. And if you do this step first, and then we'll write it out. Write it out as going, let's see, CH3, COH, and an H, and that's bonded to a CH2, and that's bonded to a C double bond O, bonded to H. These are the exact same thing, these two compounds. I just straightened out in one line. But sometimes it's easier to put the bonds in like it is on this kind of intermediate step here, and then write it out like that. Again, your beta carbon has your OH group, okay? And this is an aldol, where am I at? ALDOL, aldehyde and an alcohol. Okay, so that's how condensation reacts in aldehydes occur. And it forms what's called an aldol. And okay, so it's not going to release any of those. Oh, there it goes. It's erasing some of them. So the carbonyl carbon, the first molecule, becomes the alcohol carbon in the aldol. Okay, the carbonyl carbon. Remember, we said 1 and 2. We said this was number 1. This was number 2. Okay, the carbonyl carbon. This is your carbonyl carbon right here. Because of the first molecule becomes the alcohol carbon in the aldol, and this is your alcohol carbon right here. That's the same carbon. Okay, the alpha carbon of the first molecule. Okay, this is your alpha carbon, one next to it here. Okay, is this carbon right here? That carbon are the exact same. Those are your alpha carbon, the first molecules. Okay, and I can't even read that one. This looks at the alpha carbon of the second molecule is what's bonded right here. We've got too much stuff written on the screen. I don't think it'll erase it right now. No, okay. But we'll go through and get another example here of how that's done. It's erasing some of it. Let's get it so you can just see the last one right here. All right, let's try to go back. We'll see what happens if I go back. Okay, so here's your reaction. This is, again, your carbonyl carbon, the first molecule, becomes the alcohol carbon in the aldol. Okay, the carbonyl carbon, the first molecule, becomes the alcohol carbon in the aldol. And this alpha carbon of the first molecule is the 2 stains with the green arrows. And the alpha carbon, the second molecule, is the 2 red arrows. So you should identify where each one is being positioned as it comes across. Okay, the aldol concentration of ethanol, produces 3-hydroxy-butanal. That's what the name of this compound is right here. Okay, butanal, there's 4 carbons. Okay, 3, there's a hydroxy group. Okay, so 3-hydroxy-butane-al, all single bonds, ALN, because this is an aldehyde. Again, the aldehyde and the alcohol are 2 functional groups. Okay, the aldehyde becomes the main one because it's the most oxidized of the 2 functional groups. Standing with 3-hydroxy-butanal from the condensation of an aldehyde. All right, let's try another example here. Use similar results with aldehydes or ketones. Okay, write the equation for the aldol condensation of propanone. Give the IUPAC name of the product. Okay, so how I would do this, okay, I would put propanone, CH3CO, CH3. That's propanone. And how I do it is I write it right underneath it. It's just easier for me to see that way. And then I'll straighten it out when I'm done. All right, so there's my two compounds. We'll take this one number 1, this one number 2. Okay, so we take the alpha carbon of the second one, okay, which doesn't matter right or left, you go either one. This is your alpha carbon right here. We take that hydrogen and it's going to attack that oxygen. This double bond is going to go away here. And then this carbon is going to attach, the alpha carbon is going to attach to the carbonyl carbon. And that's it. That's what happens. And we just got to write it out. So we have CH3, C, and we put an OH up there, and then CH3. That's the number 1 part on the top. Number 2 one comes down, and that connects to the CH2, C, double bond O, CH3. And that's it. That's how it connects. You've taken the hydrogen of the alpha carbon and attached it to the oxygen on top. Then you've taken that same carbon you lost the hydrogen from and attached it to the carbonyl carbon where that double bond was lost. And that's what you end up with. Now we straighten it out. So we come out with CH3. There's a carbon, and on that carbon we have another CH3 and an OH. So OH, CH3. That connects to this other carbon, which is CH2, connects to this carbon with a carbonyl group, connects to CH3. That's the exact same thing as it's above it, just straightened out. We just put it all in one line so we can name it easier. So name that thing. We have got 1, 2, 3, 4, 5 carbons. Okay. And we have a ketone group. We have a methyl group. We have an OH group. So ketone is going to take precedence. So this is 2. I said 1, 2, 3, 4, 5 carbons. So pentanone. That's an A. So 2-pentanone. And we have a hydroxyl group and a methyl group. 1, 2, 3. We have 4 hydroxyl. So 4 hydroxyl, 4 methyl, 2-pentanone. Okay. And that's what it is straightened out. I know it seems like a lot, but if you practice these a couple of times, they do become easier. And it's a lot to take in at first. But once you straighten it out, you got 5 carbons, 2, 3, 4, 5. You got a hydroxy group, which is your OH group, at number 4. You got a methyl group at number 4, and you have your ketone group at number 2. So O and E is your ketone, 5 carbons, all single bonds. Number 2 is where the carboxyl carbon is. You have a methyl group at number 4 and a hydroxyl group, OH, at number 4 also. And again, the ketone takes precedence because it is the more oxidized of the functional groups that are present. Does that make some kind of sense? We'll do some more examples. But is that sort of making sense?
Yeah.
Okay. So we're not completely lost yet, right? But this is the last new concept for this chapter. All right, so you can see, I tend to write all over these. Let's see if I can back some of this up and get rid of some of this markings that I put on here. So you can see a little clearer. Wish there was an erase button on this thing, not just a backspace for the lines that you put on it. I really can't find one without erasing everything else that's on the screen. Okay. Get this off of here, and then we'll go through this one more time, show you the different steps involved in it. All right, get it so it's at least a little bit clear here. Okay, so this is the auto condensation, the aldol condensation, okay, of propanone. Again, propanones are 3 carbons. That's a ketone with the carbonyl group dead center right in the middle. That's the only place it can be, or else it'd be an aldehyde. All right. Give you a little time to absorb all this here again. All right, perfect. Now we can see it. Okay, so aldol condensation. Remember, aldehyde and an alcohol. Okay, so this is propanone. Everybody sees that this is number 1, this is number 2. These are the exact same molecule, right? Everybody sees the exact same thing. We just wrote out this CH3 here, and we wrote out this. We just wrote the hydrogens out so you can see them. So in aldol condensation, you take the alpha carbon of the second molecule. You take that hydrogen, okay, and it transfers and connects to the OH of the first one. That kicks this double bond, the electrons from it down to here, and those electrons attract the carbon we lost a hydrogen from to make a bond. That's it. That's the whole mechanism. That's everything. You just got to write it out. But that's what happens. Okay. The alpha carbon loses a hydrogen of number 2 to the oxygen of the carbonyl group number 1. Then that carbon is now missing that hydrogen. It connects to the carbon where the double bond was to form a new bond. That's the whole mechanism. Okay. And this is the product that you get from doing that. So how we showed it before. And to name this, there's 5 carbons, so it's pentanal, and this is 2-pentanal, and it's 4-hydroxy, 4-methyl, 2-pentanal. 2-pentanone, I'm sorry, not pentanal, so it's a ketone. Pentanone. All right. So in the laboratory, aldol condensations is catalyzed. Let's see if I can get that off. There we go. Okay, by a dilute base, but the same reaction occurs in your cells in the body when it's catalyzed by an enzyme. So we're going to be seeing a lot of these reactions when we do biochemistry in the next couple of chapters. So the reaction in one of the pathways makes a sugar glucose from smaller molecules. Okay, so it's called gluconeogenesis, the formation of glucose, because the body can make glucose out of pyruvate, smaller molecules. So the pathway is critical during starvation or following very strenuous exercise. Okay, so under those conditions, blood glucose concentration can fall dangerously low. So you have to make glucose to fill that in, either if we start starving or with strenuous exercise, depletes our glucose storage. The brain can use only glucose as an energy source. Okay, most other things use other alternatives, but the brain only can use glucose for energy. So it's essential that you be able to produce it quickly when we need it. Okay, so one of the steps in the pathway is aldol condensation that we're going to learn about between the ketone dihydroxyacetone phosphate and the aldehyde glyceraldehyde 3-phosphate. Those combine in an aldol condensation reaction to help produce glucose. That's one of the steps. Okay, so this is what it looks like. Okay, this is an enzyme that catalyzes the reaction. Okay, so we take the Okay, these are the exact same molecules just written upside down, right? So we take the hydrogen from number 2 on the alpha carbon, and this is going to connect to that oxygen. Then we take this carbon and we're going to connect it to the carbon of the carbonyl group. That's it. And that's what this forms when you write it all out together. Okay. Again, you have an OH group on the beta carbon. We have other OH groups attached to this one also. Okay. But writing it straight out, this is what we have to produce glucose. We lose those phosphate groups. And it's an aldol condensation reaction. Okay. Again, it's 2 steps, but it just looks confusing. We take the hydrogen, step number 1. Okay, take the hydrogen of the second on the alpha carbon, and it attacks the oxygen of the carbonyl group and gives you an OH. Okay. Then we take that same carbon and we attach it to the other end of the double bond of the carbon atom. And that forms an aldol. Okay, so here's the bond that's formed. This is between those two. This is this bond right here from this carbon to this carbon. Okay. So this is dihydroxyacetone phosphate, both the same thing. And then glyceraldehyde 3-phosphate. And it forms fructose 1,6-biphosphate. And that's where you use to form glucose with. We can hydrolyze that. Okay, the speed and specificity of the reactions are ensured by the enzyme aldolase. Okay, enzymes allow biological reactions to occur at a fast rate within the human body. Okay, the product is sugar fructose 1,6-biphosphate, which is converted by another enzyme into glucose 1,6-biphosphate, which gets converted into glucose for use by the brain. Okay, removal of the 2 phosphoryl groups results in a new molecule of glucose for use by the body as an energy source. Again, glucose can be used to produce ATP and is used by the brain to produce energy. So write an equation for the aldol condensation of 2 molecules of propanol and give the IUPAC name of the product. And I will just write, I'll use the computer to make it a little bit easier because when I write, it gets kind of messy on there. So propanol, first of all, is how many carbons?
3.
3. So we're going to use propanol. It's going to be 3 carbons, and it's an Al ending, so it's an aldehyde, and we use 2 of those. And you got to remember the alpha carbon is the carbon adjacent to the carbonyl carbon. That's what you need to remember. And from there, we can do this problem. So this is 2 molecules of propanol. Let's call this number 1. Let's call this number 2. And let's see how we get to our answer here. So we have the alpha carbon of number 2. We take one of these hydrogens and it gets attached to the carbonyl group oxygen of the first compound. Then this carbon bonds to that carbon. So what we have, if we write it out, is CH3. We'll keep it to the corners here. CH2C, and this was an OH, remember? So that was this carbon, and this carbon. And then that's a hydrogen. Okay, everybody see how I did that? That was in the first, that was a propanol number 1. And the hydrogen from the other one attacked it, and it made an OH group, and it left us 3 bonds to the carbon in the center. So everybody see the first step? Any questions on that step? Okay, no questions. So this one here lost a hydrogen. So this carbon attaches to right here, which is carbon, and there was 2 hydrogens, now there's only 1, so CH, and it had the CH3 attached to it. CHC double bond O. Now, let me do that a bit better. Too many. CH3, C, carbonyl group, bonded to hydrogen. That's it. That's what it's formed. Okay. That was the first step. We took the hydrogen from right here and added to the oxygen of the carbonyl group of the first one.
So the hydrogen that you need to make the second, on the second row, it's a CH3, that hydrogen just comes in, or?
No, you mean this CH3 right here?
Yeah,
That's
because I
this
thought it
one.
was gonna be a C,
That's this one right here.
right, so you take it, oh no, right, you take the H from the different, from the other side, okay.
You only take that's right. You only take. It's confusing because it doesn't look like it's supposed to.
I wrote
took-
from the first grouping, so I was thinking that there's still H2 because you took one, but I realized that I did it from this first grouping instead of the second.
Okay, yeah. Go to the second one. Take the hydrogen off the alpha carbon, and it attacks the oxygen of the carbonyl group of the first one.
Okay.
So this carbon here, let's use this. This carbon here is this carbon here. Okay, those green marks that's the same carbon. Lost hydrogen, and this oxygen, this carbon here, I should use a different color. Okay, this carbon here, that's purple, is this carbon here. Okay, that's what we've attached.
Okay.
And if I straighten it out, then we get the same product we have on the right side. We get, let's just do the top line right across here. We end up with CH3, CH2, carbon with a hydrogen, and then an OH group. I did the first line, right? This is that first line. I just copied it. Then this carbon here is attached to another carbon, which has a CH3 group attached to it, which has a hydrogen and has a carbon, double bonded to O, bonded to H. And that's the second line right here. So here's your first line, here's your second line. And that's the same right there. So once I straighten out, it's the exact same thing that they came up with. Okay, so this is just straightening it out on one line of what we've done. Okay, so now all I gotta do is name the product. So what's formed? Okay, this has 1, 2, 3, 4, 5 carbons. Right? So it's pentane, and it's an aldehyde. So let's put it down here, pent to an al. Okay. There's a methyl group at number 2. There's a hydroxy group at number 3. So 3, I already said it, 3 hydroxy, 2 methyl, pentanal. Is the IUPAC name for that thing. All right. 2 molecules of butanal. Okay, butanal is 4 carbons. So what we're going to have, we'll put up here, then I'll just put the screen down there because my writing's not that great when I start doing all these. So 4 carbons, all single bonds, butanal. It's an aldehyde. Okay, so CH3, CH2, CH2, COH. There's butanal. So there's your 2 carbons, the 2 things of butanal. Now we're going to end up with that product, but let's do it how we're supposed to do it. Let's take our alpha carbon. So here's this is number 1, this is number 2. We're good with that part, right? We can all do 1 and 2.
Yeah.
All right. And we take the alpha carbon of number 2. Remember, the alpha carbon is the one adjacent to the carbonyl group. We take the hydrogen, one of those hydrogens, let's mark it in blue, one of these hydrogens, and put it right here. That gets rid of this double bond and moves it down to here. Okay, that's the first step. Does that make sense?
Yes.
Okay, we take the alpha carbon, take one of the hydrogens, move it to the carbonyl oxygen of number 1. Then we connect the two. This carbon here and this carbon here only have 3 bonds now, right? We've taken a hydrogen away from the number 2, and we lost a double bond on the number 1 one. So these 2 carbons connect. So this carbon connects to this carbon. That's it. That's all involved. Now the hard part is writing the structure to get the final product. So let's write our structures out. The first structure is this, is CH3. Whoops, I'll go back. I didn't want to go back far. Right there, okay. First structure is CH3, CH2, CH2, C, OH, H, right? That's our first line. That's this line right here. Everybody see that? I got rid of the double bond and I put a hydrogen on the oxygen. So this carbon right here is going to connect to number 2, and it's connect at the alpha carbon. So it connects right there where it says CH, because we lost a hydrogen. So this carbon right here is where we're connecting right here. That's this carbon. Okay. To the left of it is a CH2, CH3. To the right of it is a carbonyl group or aldehyde. That's it. I've just written the 2 compounds and I've connected them. Now I just straighten it out. And when I straighten it out, I'm going to have this compound right here. This is the same thing, just straightened out. Because let's go through it. Let's go. The top line is CH3. What's that?
Did we take the carbon and the hydrogen from the second equation or second grouping because it's closer to the substituent?
Yeah, you took the hydrogen from number 2
Yes.
because it's the alpha carbon one adjacent to the carbonyl group.
Okay. I took it from the second one.
Yeah, you got to take the hydrogen from the second one and put
Okay.
it to the first one.
Okay.
Okay. And if we straighten this thing out, we have CH3, CH2, CH2, right? CH3, CH2, CH2. Okay. And then C, and there's an OH.
Oh, should you call me on his?
And there's an H.
Yeah.
There we go. Oh, an H. Okay, that's the first line. That's this line right here. Okay. Then it connects to a CH. And this connects to a CH2, CH3. And it connects to a C, carbonyl group H. That's the scene that's straightened out each line. This is the first line right here. Here's your first line. And then this is the second line below it that's connected now. And we just follow the path like that. And that's the exact same thing as written right here. Same exact thing. Okay, so now we name it. Okay, so there's 1, 2, 3, 4, 5, 6 carbons. Okay, so 6 carbons is hex. So we have this name of, it's hexane, and it's an aldehyde. So it's hexanal. Okay, is the end of it. And you have some constituents attached to it. You have a substituent here and a substituent here. So you have 3-hydroxy and 2 is a ethyl group. So 2-ethyl. Three hydroxy hexanol. Okay, so there's 3-hydroxy. I put it backwards here. There's either way. 3-hydroxy, 2-ethyl hexanal, or 2-ethyl 3-hydroxy, alphabetical order hexanal. Okay, that's IUPAC name for it. Is it starting to make a little bit more sense?
Yeah.
Okay, that's how they go. We'll finish this up and we'll be all set. So the chemistry of vision works by these same things, or these reactions. So sight is a physiological process. Depending on 2 types of cells. We have rods and cones in our eyes. Okay, rods are night vision, cones are during the day for our acute color vision. Rods see black and white, cones see color. Rods are responsible for vision in dim light, night vision. Cones are responsible for vision in bright light. Okay, that's your accurate vision. So vision in rod cells require unsaturated. Remember, unsaturated means it has double bonds, multiple bonds. Requires the unsaturated aldehyde 11-cis retinal, which is produced from vitamin A. Okay, vitamin A be obtained directly in their diet, but it's also true by the cleavage of beta carotene, which is obtained in your diet. So you take vitamin A supplements, or you can get a vitamin A from beta carotene. The body can cleave it and make it. Okay. And this is 11-cis retinal. That's what it looks like. You can see the carbonyl group. Okay. You see the detachments, the conjugated bonding systems, and the cyclical structure. So this is an aldehyde. So okay, so in the retina, there's a protein called opsin, which combines with 11-cis retinal to form a complex called rhodopsin. That's what allows the eye to see. Okay, when light strikes the rods, the light energy is absorbed by 11-cis retinal, which is then photochemically converted to 11-trans retinal. So it goes from a cis to a trans relationship when it hits light, and that's what registers in your brain as light. Causes a change in the shape of rhodopsin complex, results in the dissociation of 11-trans retinal from the protein. So once it changes shape, the protein breaks away from it. That signals the eye that light has been seen. Okay, this causes ions to flow more freely into the rod cells. Okay, the influx of ions stimulates nerve cells, and that sends a signal to the brain. Okay, interpretation of those signals produces your visual image. So that's how it works. Cis trans isometers of an aldehyde. It's how vision actually works in the eye. So here's your cis trans isomer. This is cis retinal. Okay, here's the cis relationship right here in the red circle. You can see the hydrogens are on both sides of the double bond. The carbons are on the same side. That's cis. The light wave hits it. When light activates it, it goes to the transposition, which means the hydrogen goes to opposite sides of the double bond, and the carbon on the side of the bond. Okay, that changes its shape. Look at the difference in shape. Okay, that changes shape. The rhodopsin gets kicked off of it because it doesn't hold it anymore. That changes an influx of ions, which moves, which causes you to see your visual image. Basically, it's the cis and trans rotation of the retinal. Okay, so following your initial light stimulus, it returns to the cis trans isomer and reassociates with opsin. So once you're done with the stimulus, it reattaches. It goes back to the cis isomer and reattaches with the opsin, which stops the ion flow. And then you're ready for the next impulse of light. Okay. Some of the retinal is lost in the process and been replaced by the conversion of vitamin A or beta carotene. So once some gets used up, and you got to replace it. Either like that vitamin A supplements or beta carotene in your diet, which can be hydrolyzed and converted into vitamin A. Okay. Deficiency of vitamin A can have some very bad consequences. Okay. In children, lack of vitamin A causes xerophthalmia. Okay. And eye disease that results first in night blindness and then total blindness. So it affects the rods first for your night vision, and then it starts to affect the cones. Okay. Eye disease can easily be prevented by a diet rich in vitamin A, supplements you give them, or beta carotene. Okay. So this is vitamin A, and this is beta carotene. See the similarities? And this is converted in the body to vitamin A through a series of enzymes. Okay, summary of the chapter. This is what we've done. Oxidation of aldehydes. Aldehydes oxidize to carboxylic acids. Okay, reduction of aldehydes and ketones. Ketones can reduce to a secondary alcohol. Aldehydes reduce to a primary alcohol. Okay. Addition of an alcohol, keto formations. Okay. This was our alcohols being added to a ketone. This formed a hemiketal. Adding another alcohol to it formed a ketal. Okay. There was a lot of information in the last part of this chapter. So your ketone, your alcohol, your hemiketal, and your ketal. Okay. Addition of alcohol to an aldehyde forms an acetyl formation. Okay. You've got your aldehyde reacts with your alcohol to give you a hemiacetal. Okay. It's an acetyl because there's an R and an H, and it's hemi because the OH is still present there. And you add a second alcohol to it, and it forms a acetyl group, acetyl, and then and plus water. Remember, the water comes off of there. So there's your aldehyde, there's your alcohol, this is your hemiacetal, and this is your acetyl. Okay, keto-enol tautomerization. Okay, remember tautomerization was the keto form, which is your carbonyl group. Okay, in the form of this hydrogen. Okay, this hydrogen transfers the alpha carbon, the hydrogen on the alpha carbon transfers to the oxygen of the carbonyl group, and this double bond slams down into the carbon-carbon, forming a carbon-carbon double bond. So this is your ketone, and this is your enol. Because there's your E double bond, and your OL is your alcohol. And this is used in more stable form, the keto. That's your most stable form of it. But it's a tautomerization. It's an isomer. Same thing, it's just you're moving the bonds, and you're moving one of the elements. Aldol condensation we talked about. Okay. We have two ketones in this case combined to form an aldol. Okay, there's your aldehyde or your ketone and your alcohol. All right, this is all the reactions we covered. Carbonyl groups, oxidation, reduction, addition, and aldehyde. We can form our hemiacetals and acetyls, or hemiketal and ketals. Okay. And again, that's just a way of looking at the different oxidation reduction reactions. You can go through that. Just a summarization of all the reactions that we've done. And we did aldehydes and ketones, oxidation of an aldehyde, reduction of aldehydes and ketones, addition reactions, hemiacetals, acetyls, hemiketals, and ketals, keto-enol tautomerization, and aldol condensation. There's a lot of information in today's lecture, a lot more than we usually cover. And it's a lot of different types, but go through it. Questions, ask me. And I think that's the last slide. Again, our summaries of reactions again. You just use these to review the different types of reactions that we've done